So, without further ado, we are going to get started. So now that my colleagues did like the most boring 2 sessions in a row, apparently that's what they claimed, I'm going to do a one a little bit more exciting, one about transactions. Actually, there is some overlap here with what Carlo explained a couple of days ago. But it's good because transactions are very important. And why are transactions very important? Because they are what makes the chain move forward, the state to change. And so, yeah, let's get started. So we're going to look at transactions. We're going to be, before I move forward, just a huge overview of what we're going to look at. We're going to look about what things does the JSON RPC spec offer us for transactions. And then we're also going to try to understand what transactions are, different kinds of transactions, what are the states, and what are the implications for users, for dApps. Okay? All right, let's get started. So if we look at the JSON RPC for transaction, there is like this group. Remember that we said like there are these groups of functions, and then the nodes have to implement either all or nothing about that group of functions. So there is actually a group of functions called transaction. And by the look of it, you'll think that this session is going to be like super, 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 super short, because there are only two methods, broadcast and stop, right? So yeah, welcome to my tech talk. See you. No, just kidding. It looks simple, right? But it's not, because there are certain challenges. The first challenge is creating a transaction. Creating a transaction is not easy. It's not straightforward. Like you are going to be using a library that helps you to create transactions, but it's important that you understand how these transactions are being created, because there are different kinds of transactions, and also depending on how a transaction has been created, and we'll get a bit we'll get deeper a bit later, but like depending on which kind of extensions do they have and whatnot, you can have different kinds of invalidity errors. You can like, long story short, it is good that you treat transactions not as a black box, but as something that you at least understand a little bit how it works and what's in it. Okay. So creating a transaction is not something straightforward. Then we have another challenge, which is validating a transaction. As you'll see, validating where a transaction can be. Remember that in the previous slide we had like these two methods, broadcast and not. Well, so validating a transaction, which basically means like, can we broadcast this transaction, is also not straightforward. And if you broadcast transactions that cannot be broadcasted because they're invalid, then nodes are going to block you. They're going to block your IP because they're going to think that you are a malicious actor, and that's not good. You don't want your dApp to get blocked and not being able to submit transactions, right? Then we have another challenge, which is like tracking transactions. Like, okay, we have created a transaction, we have validated, we have broadcasted. Now, what's going on with this transaction, right? When did it get included? Is it included in a finalized block? Is it included in a non-finalized block? Got included, but it failed. Oh, it became invalid. You'll see that there are lots of different states, and which is what I'm talking later, which is the different states that a transaction can be in. Okay, so let's get started. Okay. All right. First things first, we need to understand the different kinds of transactions, right? So in Polkadot, you'll hear this term a lot, right? You'll hear the term extrinsic. Have you heard this term before? The term extrinsic. Who can tell me what an extrinsic is and why someone picked this name? Does anyone want to give it a shot? Maybe they will teach me. It's very possible. Can someone tell me what extrinsic means and why?
It's a transaction with extra signers. I mean, extra options.
Actually, no. But that's what I thought too, actually. because you see, like everything is extrinsic. So we have signed transactions, which these are the ones that have extra stuff, right? Then we have unsigned transactions, which usually they don't have extra stuff because they are unsigned. And inside these unsigned transactions, there are these kind of unsigned transactions that are called inherent. So I always thought, oh, because there are these inherent, like inherent is like from the inside, so extrinsic must be from the outside, right? And in my head, I kind of thought like extrinsic are what you said, the signed transactions. That's what I thought. Well, no, extrinsic is just a generic term for transaction, because if you look at this box, what it says is that an extrinsic is anything inside this box, whether it's signed or unsigned. So it's a fancy, I don't know why it was chosen. I guess that it was chosen to kind of distinguish ourselves from other ecosystems, because like we have different kinds of terms. I don't know why this term was chosen. But the point is that an extrinsic is just a transaction. And inside transactions, we have two different kinds. Signed ones and unsigned ones. So you as a user, there are a few unsigned transactions that you can make. I think that one of them is, I'm not sure, but I think that rebugging someone could be done, no? Is there an unsigned transaction that, yeah. Like the initial transactions that were done at the beginning of the blockchain for claiming your dot from for those had to be unsigned because you still didn't have dot in there. Yeah. So there are certain yes.
Or the one I mentioned when upgrading the code, essentially. So you
Oh,
do
yeah.
a
For a
Python
code
upgrade that's
yeah.
signed, but then you
Yeah.
upload the code with
Yeah. That can be an unsigned transaction.
Or
So
the
like,
biggest example we gave was the Palette Revive Ethereum transact.
absolutely right. Like the ones for Palette Revive are unsigned transactions, because basically they are unsigned transactions that inside the payload of the call data, they have kind of in there embed like like the Ethereum-like transaction that gets evaluated by Revive and whatnot. So like it is kind of signed, but at a different layer inside so like kind of boxes inside of boxes, which is an expression I use a lot, and my colleagues like to laugh at me when I use it. But yeah, so long story short, we have like these signed transactions, which are conventional transactions, and signed transactions, which means like from the transaction from the outside, like everything is just payload with no signature. But sometimes inside this payload, there is a signature, but it's handled by the business logic. And sometimes actually there isn't. Like what is someone is making from the outside? Okay. Okay. So we have signed transaction, and then there is this special kind of unsigned transactions that are called inherent. Who can tell me what an inherent is? No, it's okay. You don't know. It's fine. I wouldn't know either. I'm going to show you an example of an inherent. These inherents are normally transactions. No, not normally. They are transactions that are being included there sneakily by the block author and that are supposed to be there. So, for instance, if we go to dev.how, it's using small dot, so it'll take some time to connect unless I switch. It wasn't that bad. So if we look at the block, so you see this. This is an extrinsic. You see, it's timestamp set. So timestamp set is it's a transaction that was created by the block author. Whoever authored that block put that transaction there just because they want it. So basically, inherents are one kind of unsigned transactions that have never gone through the transaction pool, if you may, right? Like if you think about it, all the other unsigned transactions, they get gossip, they get passed around and stuff. The inherents are like one special case of unsigned transaction that doesn't go through the transaction pool, and the main reason is because it's the block author, the one that puts it there, right? Okay, but all these are referred as extrinsics. But very often, we just don't use that word, and we just use the word transaction, because as you can see, everything is transaction. But just for you to know, whenever you hear the word extrinsic, because there's also a field inside the header, it's called extrinsic root, which basically is like the Merkleized version of the transactions that are in the body. It includes this, right? It's any sort of transaction that that was in the block body, right? Okay, so the other important thing to take into account is that when a block gets evaluated, the transactions get evaluated sequentially, right? Like so, and that each transaction creates a new state, right? So there are intermediary states, but what it gets reflected into the block header is the final state after each transaction is executed. And that's what we see in the state root hash. All right, let's move on. Now we're going to discuss, actually these days we have extrinsic v5, but we're going to discuss extrinsic v4 because extrinsic v5 is not that different. And conceptually speaking, the concepts that I want to explain here also apply to extrinsic v5. Carlo already gave you a little bit of an overview of extrinsic v5 and about why doing it there and whatnot. But we're going to try to keep it simple because it's more important that you understand the basic concepts, and then from this you probably get the abstraction, and it will be easier for you to understand extrinsic v5. Okay, so in extrinsic v4, remember, like the previous slide, we had like two different kinds of transactions, signed and unsigned. Unsigned are super duper simple. They only have like one byte. Here, this byte indicates. I'm doing something wrong with the microphone. This byte here indicates whether it's signed, unsigned, and the version, right? And then we put the call data directly. The call data is, let's go back to the console so that you see when I talk about call data, so that you know what I mean by call data. Here, I'm going to create the call data for balances, transfer, about that, destination, account ID, this one, value, blah. Okay, so this here is the call data, right? The first byte, yes, sorry. Stop looking up. So when we create get out of here. Maybe I went too far. Hold on. All right. So when we create a transaction, right, we go and we say, hey, I want to make this call, right? I want to call balances transfer. I want to go to that palette, and I want to use the transfer out there, and these are the arguments. So the call data is this block here. As you see, like the first 2 bytes, you see that 05 indicates the palette. This 05 here indicates the palette balances. The 00 indicates transfer allowed depth, because that's the index, right? Like if we pick another index, it's sorted alphabetically because someone asked for that. But like the point's like, you see, if I pick another index, then it's 03, and then if I change the destination, it's something else, right? Like so, this block here is the call data. It's like which palette I want to call, which method inside that palette I want to call, and which are the arguments that I'm going to pass, right? That is, when we say call data, we refer to this, right? But there is a lot more to that we pass to a transaction, as you will see in a moment, and there is a lot more that we sign. Okay, so, and then sign transaction, it's just that. It's just the call data. It's like a byte that says like I'm unsigned, and in extrinsic v5 actually it's also just 1 byte too. But it's basically a byte for saying like I'm unsigned and this is my version, and next the call data. That's simple. Signed transactions. Signed transactions are a little bit more complex. Signed transactions have an initial byte that says its version and that they are signed. Then they include the address or the public key. Well, it's technically the address, not the public key, but we'll see the difference later. The address of the one that is signing the transaction. Why is it important to have the address here? Someone can tell me? Can someone tell me why it's important to have the address here?
To know who sent the transaction.
Mostly is to verify the signature, right? Because like the signature is signed with a private key, right? And you want to see if that private key matches with whoever signed it. So you need to know like who am I, who is it that claims to have signed this stuff, right? Now, question for you, I don't know if you remember, is that in Polkadot we support 3 different kinds of schemes: SR, ED, and ECDCA. Now, do we need this one for ECDCA? ECDCA? Well, you know what I mean.
S.
ECDCA.
DS.
We actually, so we need it for consistency reasons and for something that we'll see later. But like, if you think about it, that's a signing scheme that the same signing scheme with the signature, it's already telling you the public key. So someone could claim, oh, if you're going to create a chain, because Caldo told us not too long ago that such chains exist. For instance, Moonbeam, their signed transactions are exactly like that, but they only allow for one signature scheme, which is ECDSA. Anyways, that one. They only allow for that one. And someone could be like, these people are wasting a lot of bytes on each transaction because the address could be derived from the signature. And they will be right. It is true. They are wasting bytes in every single transaction. And if you wonder why, it's because frame is customizable, but if you want to become interoperable with all the other transactions, it's not that simple. So that's why they kept it. Anyways, just like a side note, like, but the reason why we need the address here is because not all signature schemes allow us to derive the public key from the signature. Some do, some do not. And the one that's most commonly used in Polkadot, which is SR 25529, no, 2519, whatever, SR, I always call it SR, does not allow us. Okay, so we have the first byte that it's letting us know it's signed. This is my version. This is the address from which you have to somehow get the public key to verify this signature. Yeah, this is a signature. This is the extra. We'll see what this extra is, and this is the call data, right? So why do we need the? If you think about it, forget about the extra one moment. We'll see what the extra is in a moment. But if you think about the call data, the reason why we need to have it here is because a signature is not decryptable. It's like this. I've seen so many people struggle with this, right? A signature is you are proving that you signed a message, but from the signature you cannot decode the message. You cannot decrypt it, right? It is signed with a private key, right? But it is a one-way function in that regard, right? So a signature is a proof that I approve this message, right? But I need to tell you what the message is. With the signature itself, you cannot find out the message. Does that make sense? I suppose that you did like basic cryptography and whatnot, and that this is very basic. But like some people get confused with this because just because it's signed with a private key doesn't mean that it's that you can decipher it. Someone needs to tell you what is that got signed. Does that make sense? Yeah. Okay. So we need to have the call data to verify that this call data has been signed and it's included here. And now we'll see what the extra is in just a minute. Okay. All right, so as we said before, what is being signed? The call data, for sure, we need to sign it. And then this extra thing, which is part of what is inside the sign extensions. Okay, The call data, I already explained before. It's the information that is needed to execute the call, right? Again, we explained before, the first byte indicates the index of the pallet, the second byte indicates the call itself, and the remaining bytes are the arguments, the incorrect arguments of the call. So far, so good. If anyone has questions, please let me know. Okay, sign extensions. Sign extensions are only available for signed transactions because they are called sign extensions, right? So sign extensions are functions. So when you have when you have your frame runtime, you can define like these sign extensions that will be used for, at least in version 4, that will be used for all transactions of that runtime. And these functions get executed for all transactions, and they get evaluated prior to the evaluation of the call data. Basically, each sign extension has kind of two hooks. One, for validating the transaction, and two, once the transaction has been validated, it's the logic that it will be applied prior to the execution of the call data, right? It's some sort of logic. So first, they all have a method that allows the node to tell the node before you actually go and execute this transaction, come to me and check. I'm going to tell you if this transaction is valid. You shouldn't be wasting resources otherwise, right? And if the transaction has been deemed valid, and it can be included, because not all valid transactions can be included, as we'll see in a moment, then the node, when it executes the transaction, is going to run the other hook in the sign extension that allows the sign extension to execute cross-cutting concern logic, basically some logic that kind of applies to all transactions. A good example, how like there is a sign extension that is used for one, validating that the person, the address that is signing the transaction has enough funds for paying for the transaction, right? But also this same sign extension, if the transaction is invalid and it gets executed, this sign extension is the one that first removes the funds from the user prior to executing the call, and then once the call is executed, it keeps track of how much resources it has, that this execution has taken, and then after the execution, it returns to the user the reminder. So it's like the way that these work in Polkadot, they work with weights, which means that each call that we have, each call that we have in each pallet has some weight, and the weight is like the worst case scenario. In the worst case scenario, this transaction is going to take this amount of weight, and this weight gets translated into fees, right? So there's a sign extension that first checks, okay, they are trying to execute this call data, all right? For this call data, what is the worst case scenario? How much weight is this call data going to take in the worst case? It's going to take 5 dots in the worst case, and this user only has 2 dots. Therefore, this transaction is invalid. Now, this is what is a little bit tricky sometimes. Sometimes there are certain transactions that if you had more dots, right, the transaction in the end will only cost like 1 dot. But this happens when we do like a complex batch with a lot of things, right? The sign extension checks and it looks at the worst case scenario. And if you cannot pay for the transaction in the worst case scenario, this transaction cannot be valid. It cannot be included. But sometimes it turns out that when it's included, it costs a lot less. So it kind of seems like, oh, you actually didn't need that much, but you did. So the only way to work around this is instead of putting them into a huge batch, like execute them in different transactions, basically. Anyways, that was a bit of sign up, but I was just wanting to understand that sign extension play 2 roles. One, help at determining whether a transaction is valid, and if a transaction is valid, whether it can, like, if a transaction is not valid, it cannot be put into the transaction pool, and it cannot be evaluated. It's like, we cannot broadcast this transaction. We need to forget about it, right? Until something changes, and then maybe the transaction later is going to be valid. And if it's valid, it also has some application logic that it gets applied before the execution of the call data, right? And a good example is for charging fees and returning fees, but there are many other examples, as we'll see. Okay, so chain extensions are functions that get executed for all transactions prior to the execution of the call data. They play two important roles. One, perform checks to determine whether a transaction is valid, as we explained before, and provide transversal logic to the execution of the transaction, as I just explained. Okay, so this is actually very important because a lot of people get confused between invalid transactions and failed transactions. Follow us. Because let's think for a moment, right, about what we just explained. The evaluation of the call data is not taking into account for determining whether a transaction is valid or is not invalid. Yeah. So let's think this. Let's see what the implications of these are. What happens if I have 5 dot in my account? I have 5 dot in my account, and then I create a transaction with a call data that it's like send Victor 10 dot. And then I create this transaction, I sign it, and I broadcast it. Is this transaction valid? No. Why not?
Because you are sending 10 dot and in your wallet there is only 5 dot. So
But didn't we just say that the evaluation of the call data is not taking into account for determining the validity of a transaction? That's evaluating the call data. You're cheating. You're evaluating the call data. So this is the key. This is what can be tricky. One thing is whether a transaction is valid or not, whether a transaction can be included into the chain and can be evaluated. And the other thing is the outcome of this transaction. Yeah. So intuitively, everyone will think, well, I mean, let's be real. In reality, if you try to create such transaction, your wallet, if it's a decent wallet like Talisman, is going to tell you, dude, I can sign and create this transaction, I can broadcast it, but you will just be wasting fees because this transaction won't execute. I mean, will execute, but you won't have the effect that you wish, right? So let that sink for a moment. The evaluation of the call data is not taking into account for determining the validity of a transaction. So basically, you need to look at transaction as these two different layers. The validation layer is like kind of a quick sanity check, right? Like, have you seen that meme of like that guy working like at a football stadium, kind of scanning people like this, like to check if they have. That's checking if a transaction is valid, right? Like if I see the guy wearing a bazooka and a visible gun and stuff, I'm not going to let them in because it's obvious, right? But the checking if a transaction is valid is a very superficial check. The only thing that we want to know really is, can this transaction do something that is insecure from an economic standpoint? Like, for instance, like if the user doesn't have enough funds for paying the transaction fee, right? Like, why will even bother to check the call data, right? Like, they cannot pay for this transaction. Like, I already look at the weights, they don't have enough, out, right? But if you want to create the call data that's like, oh, I'm going to send like a gazillion tokens to these guys, right? Do you have enough fees to pay for this? Yeah, okay. Have you signed it? Okay, yeah, sure. We'll put it in the transaction pool. Then what happens is when the transaction is actually included in a block and it gets executed, the execution will be like, whoa, whoa, whoa. They're trying to send more to this guy that they have. Then the transaction fails. But this is the difference. When a transaction is valid, the transaction gets included into the chain, right? It gets included into the block. And then the transaction may fail. Is there something that you want to comment, Carlo? Okay. Then the transaction, so this is the thing, right? The validation of a transaction, and this is important, right? Like the validation of the transaction does not take into account the call data. The call data is like kind of this black box that only if the transaction gets included into the block, then it will be evaluated, right? But for determining whether a transaction is valid or invalid, we don't look at the call data. We look at other stuff. Does that make sense? Okay. So there was a question about mortality. So if you want, we can do a little bit of a deep dive into mortality. Because it's actually a very cool sign extension because as we will explain here, each sign extension, I'm going to explain this and then I'm going to go back to mortality. I'm not forgetting, but like I think it's important we explain it, right? When we look at the sign extension definitions in the metadata, we'll find that each sign extension has, in their definition, it's like, it has two different fields. One that is called extra, and the other one that it's like the implicitly known data. You will see different names in different places for these kind of fields, but for all purposes, we're going to refer as one field as the implicitly known data. This is data that the chain already knows about and the user doesn't have to provide. The user assigns this data, but you don't put it in the extra. It's like the same way that you put the call data because the chain needs to know the call data, and you put certain information about certain sign extensions in the extra, that this is implicitly known data, like the Genesis hash, right? It will make sense to sign the Genesis hash and also put it after the signature because, well, the chain already knows what the Genesis hash is, right? Like you don't need to tell it, right? So there is implicitly known data and extraneous data. This is the extra field. This is information that the chain cannot know. The chain cannot know implicitly, right? Like the tip, for instance. Or in the case of mortality, the chain needs some sort of way of knowing until when you want this transaction to be valid, right? So mortality is kind of an interesting sign extension because if you look at the definition, conceptually speaking, what you need to understand is that mortality, what it does is it tells the chain, it tells the runtime until when this transaction is still valid. If it's immortal, it's valid until the end of time. If it's immortal, it's valid until a certain height. However, because in Polkadot, like we're super clever people, that's not what we pass into the extra field. And you'll see, it's actually very cool what we pass. So here are some examples, as I explained. The nonce is the only one that can be a little bit trippy. I'll go back to mortality in a moment. But the nonce is the only one that can be a little bit trippy for reasons that we have already explained, which is like the nonce, it looks like the chain can infer it because the chain could actually check it from the state, which one is the current nonce. However, if you want to send many transactions at once, so like you have created a transaction, you have broadcasted, and now you see, oh, I want to create another transaction, I want to broadcast it. You don't want to wait until this transaction is actually in a finalized block. You may want to create a future transaction. So you need to provide the nonce, and then when the transactions get into the transaction pool of the node is going to sort them and put them in the right order, right? That's the only reason why we need to provide the nonce, right? Other examples of extraneous data are the tip, like how much tip I want to give to this validator for prioritizing my transaction or for being so nice that they are including my transaction to the chain. And in some chains, we also have the asset, which is in which asset we want to pay for this transaction, which is something pretty crazy. If you think about it, right? Like you may not have enough, like for instance, in Asset Hub, maybe you don't have enough DOT, but you have enough USDC, so you may want to pay the transaction in USDC or in USDT. And in reality, what happens behind the scenes is that there has to be some sort of swap mechanism that allows to swap this asset into the native one, but you as a user can even if you don't have the native token, as long as you have enough of the asset that you want to pay the tip with, you can pay the transaction with that. So something cool with that is that if someone wants to send you USDT in Asset Hub, even if you don't have an account on Asset Hub, they can send USDT to your account on Asset Hub. And even if you don't have a single dot, you can still create transactions on Asset Hub with USDT. As someone that has come from Ethereum, I find this like incredibly valuable because like at least back in the days in Ethereum, like you could have a shitload of ERC20 or whatever, but if your ETH went below the minimum that's needed for paying the transaction fees, good luck. You can just stare at all your beautiful balances in the ERC20 and until you find a way to get native ETH into the chain, you won't be able to do much. So it's actually pretty cool. Anyways, so these are some examples of information that we may pass in the extra field, okay? Now, the check mortality is actually very crazy. And because some people ask, we're going to do a deep dive. Now, you'll learn not to ask certain questions after this deep dive, but no, just kidding. But let's check what happens when we look at the metadata for check mortality. So here, okay, this additionally signed is the implicitly known data. So this implicitly known data is the hash 256. This is the block hash. I will need this now. Hold on a second. I mean, the first time that someone explained mortality to me, I was like, oh yeah, it won't have any, like, I will imagine that it won't have any implicitly known data, and it will only have explicitly known data, and the explicitly known data should be the maximum block height that I want, right? Is this good here? Can they see? I need to stop sharing. Okay, before I stop sharing, I wanted to show the type of, okay, fine, whatever. I'll explain it in the board, whatever, fine. Stop sharing. All right, and now I need to erase the board. Okay, I'm sure I'm going to make a mistake when I explain this, but like, no, probably, I don't know if I will, probably won't. But, because I didn't prepare for this, but okay, so mortality, right? Let's imagine that All right, let's imagine that mortality is pretty cool because it can be used for different things, right? So the first thing that is pretty cool about mortality is that if you think about it in a naive manner, right, you may think like, okay, the only thing that we need to send to mortality is the maximum block height at which we want for our transaction to be valid at, right? Like, and then that's it, right? But check this out. This is the blockchain, right? These are some blocks that got finalized. Up until here, everything is final. But these ones, these represents a fork. Yeah? So in this case, in this fork, I'm exaggerating it a little bit, but you see, this will be the best block, right? But these things happen sometimes. But this is the best block. This is the one that is most likely to become final. But if a couple of blocks appear here, then that one will become the best block. And eventually, all this stuff is going to get trimmed because there is going to be finality probably will come here first, and we'll know these branches to be disregarded, and so on and so forth, right? So sometimes when we create a transaction, we want to create a transaction that is like, hey, I want my transaction to only be valid, not up until this height, but also starting at this block, right? Does that make sense? It's like, imagine that you are, you're doing some arbitrage, right? Like you have like some logic for doing arbitrage and whatnot, and you see that in this block here or in this block here, it doesn't matter. In one of these blocks, like let's keep in mind that even if these two blocks have the same height, they could have completely different states, right? Like there could be a set of transactions here and a different set of transactions here. So we have different universes, right, of different states. So it could be that you detect a state in which is like, oh, this is interesting. If this block gets finalized, if this block ends up the one becoming the canonical one, I definitely want to put a transaction here. So you don't want to put a transaction based on this block, which is the currently finalized. You want to be able to say, no, my transaction starts being valid, not at this block height, whatever, but my transaction starts being valid at this block. And if this block becomes pruned, then my transaction will be invalid. I'm fine with that, right? But at this point in time, the point of view of your node, if you create a transaction on top of this guy, or on top of this guy, or on top of this guy, these transactions are potentially valid because any of those blocks may end up being part of the canonical chain, right? Does that make sense? So you may want to create a transaction that it's like only include this transaction in the chain if it's a descendant of one of these blocks, right? So mortality is a sign extension that allows us to do that. And the way that it allows us to do that is actually pretty cool. It has two fields, right? The extra, which is extraneous data, right? It's like stuff that we have to provide outside of the signature, right? And like all sign extensions, they have extra and implicitly known data. In some sign extensions, so there are some sign extensions that, most sign extensions, sorry, they have one or the other, right? Like for instance, check Genesis hash only has implicit data, right? Because there is nothing extraneous to pass. Or charge transaction asset, only extraneous data, right? Mortality is one of the few sign extensions that uses both. It has one part that is implicit and one part that is explicit. What goes into the implicit part is the block hash, not the height, because from the height there could be many different ones. So in the implicit, we put the block hash at which we want our transaction to be valid from, right? So it's like we're telling the node, my transaction can only be valid as a descendant of this one. And now the mortality starts. Now we have to say for how many blocks is going to be valid. So what do you think that we have in the extra? What field do you think, intuitively, what do you think that we'll put in the extra? Like here in the implicit, we put the block hash. What do you think we put in the extra?
The number of blocks, maybe.
The number of blocks?
Yeah, of block.
Okay, the number of blocks. Someone said the number of blocks. Now, remember, what is implicit, you need to know up front. How can you just knowing the number of blocks, figure out the block hash. Someone tells you, because they have signed something, and in the implicit, they have put the block hash. Now, you, the node, needs to find out, because you need to verify the signature, what the heck this block hash is. So they do something that it's crazy. Like, to me, it looked like magic. It looked like this is like some serious black magic. Instead of passing the number of blocks, so first off, when I saw mortality, I assumed that everything was going to be extra, and that we were going to pass in extra was going to be the block hash, so that, you know, like, hey, it starts being, like, I need to tell you, like, I'm going to send the block hash, right? So I need to tell you, it's this block hash. And then the height, like, for how long. But instead, the block hash is implicit, so that we save bytes when we create the transaction. We sign the block hash, but we don't pass it in the extra. So what do we pass in the extra? We pass something called the period and the phase. And this uses modular math to figure out the block hash. Basically, it's like, even if I see all these nodes, the period tells me, like, for how many. The phase tells me with the chunk. You need to imagine from the beginning of the blockchain that it was created, like every n phases, right? Like, we're going to, it's modular math, basically. I'm not going to pretend that I remember how it works, although I did the decoder, so I should know. But basically, like, there are all these phases. Maybe Carlo, who is a mathematician, can help us. Like, there are these phases, and the period lets us know from this phase that we're in how much we have to go down.
Well, it's the opposite. So the period is like the chunk length.
Yeah.
And the phase is how much it moves up
Yeah.
and down.
It's the other way around. But long story short, it's like, basically, but the good thing about this is that we pass very little information, and with this little information, the node can, in a super efficient way, know, like, okay, this period tells me where do I start, and then with the phase, I go down, and then that block is going to tell me the block hash, right? So that's how it finds out the block hash, and then it also knows for how long it's valid, which is crazy, because the period is one is a U16 and the other one is a.
I'm not really sure. So
We can look in the metadata, I guess.
The only thing is, I think the period is a power of 2, right? So, yeah.
Right, because it's actually put in an enum. So one of them is a U8. One of them is a U8, which should be the period, I suppose. The phase. Yeah. True. They're powers of 2. So basically, every time you express a period, you express it in a power of 2. So by doing that, yeah. So basically, with using, long story short, using a U8 and a U16. No, another U8, I think. Both are U8s, yeah. So basically, using 2 bytes only in the extraneous data, we can mathematically know exactly, right, because yeah. Long story short, using modular math, we can pass like 2 U8s to know where do we have to look back. That will tell what is the implicit block hash that it's been signed, so we can check. And then also we know for how long it's going to be valid. So it's like pretty crazy. It's actually pretty cool. Like, so yeah. I don't know if that makes sense, but that's how this sign extension works. I didn't want to go that deep into the rabbit hole, but as you can see, I didn't prepare this. But yeah, someone asked, so.
Is it more or less clear how this magic works? I can try, maybe?
Yeah.
Okay, so the idea is like we have like the genesis block, which is like in block 0. And then we have like all of the blocks until you can think of it like this is our block with the block hash that's implicit, yeah? And let's say that this is block 1008. Okay? So what we can do here is, how do we how do we identify that we started this block hash, specifically this block hash, not this one or whatever, this block hash without saying the block hash, right? And we want to say a validity, but let's say that we want this transaction to be valid for 100 blocks. Yeah? It needs to be a power of 2, but I don't want to do like let's just make it easy and say like I want to make a validity of 100, and we can remove this power of 2 shenanigans. Okay, like the power of 2 is just like to make it a bit more efficient, more compact, and whatever. But let's say that I want to do like 100. Yeah. So what we can say is like, okay, I want my period to be 100. So it's going to be periods of this length. Yeah. But then how do we figure out this 1008? For this, we use a phase, right? So the idea is that if I divide like all of these blocks by the period, which is 100, what I will receive here is like 0, then 100, then 200, and then up to 1000. But I don't want 1000, right? I want to say that I want this block. So this is when I use the phase, and then I say like period is 100, and phase is 8. So this way, what I'm doing is like shifting all of these positions just by 8. So now it would be 8, 108, 208, and so on. And then here, what I will have is 1008. Yeah. Now, how does the blockchain actually verify this, right? So when it receives a transaction and it checks the mortality, what it receives is the period and the phase. Yes. So if it's inside here, it will say like, okay, I'm in block 1020, I don't know, right? Then it will do this like modular arithmetic, whatever, that it will subtract the phase and then divide by the period, and it will see that the start of this period is this one, and then it will check what is the hash of this block, and it will get it, and then yeah. So what it means that it's implicit is that this thing is not like, you don't see the hash, but the signature result has this thing inside. So when you want to verify, you need the node verifies the signature using this hash, and then if it's equal, then it's like, oh, then this transaction is valid. Yeah. What happens if it receives the transaction at this point, which is 1120? But then what will happen is that when it applies this period and phase, what it will find is that this is like 108. But now this is a different hash. It's like hash 2. And now when it verifies a signature, it will find that using this hash 2, it doesn't match with the signature that was actually there.
And it becomes invalid.
And then it becomes invalid, yeah.
So I don't know if this is really a question, but it sounds more of a, this could be really useful for indexing and very quick information gathering from a specific block based off of using the 2 extras and then the hash itself. I don't know if that's really a question or more so of a statement,
So
but that's kind of what I'm imagining.
The main point to convey here is that using the period and the phase, for a range of blocks, right? Because these are all the blocks that the node has in memory. Right? Like these are all the things that it has. So for all this range, it will always deterministically point to the same block hash, right? Because using this modular math that Victor explained, as long as we're in this range, I will always point to this block hash. So because I point to that block hash, the user has signed that block hash, I verify the signature, it's good. But eventually, like I'm going to, as more blocks come in, these blocks will make me point to a different block hash. And then is when the transaction becomes invalid. Does that make sense? So it's like the check mortality, it's very cool because like adding very little information into the extra, we are accomplishing 2 different things. One, determine until when this transaction is going to be valid, and 2, making sure that it's only going to be valid after a certain specific block. Does that make sense? And the only thing that we need to put in the extra is 2 UH, 2 bytes. And what gets signed, it's the block hash. The block hash takes a lot of bytes. It takes 32. So you don't want to have the block hash in the extraneous data because it takes a lot of extra bytes. So like, so if you can implicitly put it into the signature, what you're doing is super efficient. Does that make sense? So this is like the check mortality, to the best of my knowledge, is a sign extension that for some reason, I don't think they have it. I'm pretty sure they don't have it in the field. But like, I think Poco was one of the first networks to use this. Could be wrong, but I haven't seen it anywhere else. And when you look at it and you understand it, it's like it's crazy because like the little amount of information that you need to convey, that you need to pass in the extra, that allows for the node to figure out so much stuff in such a performant manner. It's crazy. Basically, it's very well thought.
My question is, using just the extra information, can you make a very efficient searching mechanism using just the blocks to identify the block hash?
Yeah.
If the block hash is somehow paired to that, you can
Yeah.
link specifically to that very ancient information.
Yeah.
Very
Yeah.
efficient, quickly doing that.
Yeah,
Can you?
in fact, Papi does that. Like, in fact, I mean, as we'll see in a moment, Papi, before it broadcasts a transaction, Papi needs to make sure that this transaction is valid, right? And a transaction, as we will see in a moment, we're getting ahead of ourselves, but a transaction is always valid when compared with a block, right? So a transaction, for instance, this transaction that I explained here, let's imagine that I create a transaction, right? Like that I create a transaction like the one I explained here, using mortality, putting this block as the implicit block hash, right? Where the mortality of this transaction starts, right? So if I validate that transaction against the currently finalized block, the transaction is invalid because like I don't know about this. So I'm going to, if I validate it against this one, I'm going to try to find the block hash that doesn't match, so the transaction is invalid. If I try to validate it against this block, the transaction is invalid. But if I validate it against this block or any of its descendants, then the transaction is valid. So what it's important to understand is that when we determine the validity of a transaction, we determine the validity of a transaction against the current state of the chain. In fact, a transaction inside the same block could be valid at the beginning, it could become invalid in the middle, and so on and so forth. Like, because like, imagine, right? Like if first you put a transaction that if you create two transactions with two different nonces, and the first one is like transfer all, allow death, and then you have another transaction that it's do whatever, well, because you've done a transfer all, allow death, and your account doesn't have any funds, so then the next transaction is invalid, so we won't get included into the block. Does that make sense? So like a transaction is always validated against a particular state. It's not like, so we need to pick which state, right? So okay, why did I explain that? Because Papi internally keeps track like of which are the known blocks that we know, where they're finalized, where they're forks, where they're a best block. Like as long as these blocks have not yet been pruned means that if finality comes here, all these blocks get pruned. Like we don't care anymore. So as long as the blocks are potentially, as long as Papi keeps track of all the blocks that can potentially be part of the canonical chain, right? So when we validate a transaction before broadcasting it, we have to make sure that this transaction is valid against one of the possible blocks, against one of the possible states. So one of the things that we have to do, and this actually, I don't know if you remember, but like the other day, like Victor said, like, oh, like for some reason, this transaction, like, anyways, there was a situation in which he requested funds from a faucet. The faucet said, yes, you have these funds, right? And then he tried to create a transaction, and the transaction was invalid because of payment reasons, right? So what I said, if you remember, is like, this shouldn't have happened because if Papi have seen the block at which the transaction is valid, even if it's not finalized, then this transaction should be broadcasted and should be deemed as valid. That should only happen if we don't know about the existence of a possible block where the state makes the transaction valid. So PAPI does that internally. PAPI, not only PAPI, well, actually, I think it's the only library that does it because the other ones rely on RPCs, which actually have a lot of bugs with this regard, and I can explain that later. Like the RPCs, they fucked up quite a lot when you try to put a transaction that it's on the tip of a block that it's not finalized. But anyways, like PAPI does that internally. Like PAPI kind of checks whether this transaction can be valid, and in order to check that, we need to look at the mortality. It's like, oh, this transaction is mortal. Let me check. If it's immortal, then I don't care against which block. I just going to validate it against the ones on the tip. But if it's mortal, then I need to find the block hash that it's referencing. If I don't have it in memory, or I don't have in memory any of its descendants, I cannot validate it. Right? So for me, at this point in time, this transaction is invalid. But if it is there, then I validate it against those blocks, and if it's valid, then we broadcast it. Hopefully that makes sense. But yes, it's done in a very, very efficient manner. Yes.
I have a question more about like, this might be not the right time, but for transaction pools, like if you have maybe a bunch of, let's say worst case or something, you have a bunch of immortal transactions that are pending. Is there ever a point where it's just there's a transaction overflow, like there's too many transactions pending in a memory pool to?
That's a good point. So I think it's important that we distinguish between what is part of the consensus logic and what is part of chain, if you want, or like what I'm trying to explain here is that in an ideal world, there will be many different node implementations, and some nodes will be better than others. And if one node has a bug, like the one that you described, that would be a bug, by the way, then the other ones wouldn't have that bug, and the network will keep producing blocks like nothing. But going back to your question, because these days Pocout only has one implementation of a node that can produce blocks. If there was a bug on the logic of the transaction pool of said node implementation, then yeah, the network will halt. So yes, like node implementations, they have to be actually very careful with all the logic that has to do with dealing with transaction pools, because it is a vector of attack, right? Like another possible vector of attack is not only a lot of immortal transactions, but what if I create like a gazillion transactions that skip my current nodes, right? Like my current nodes is 2, and I start creating transactions starting at about 4, 5, 6, 7, 8, 9, 10, right? Like all these transactions are valid, but you cannot include them because you're missing the nodes in between. And I will spam you with like all these valid transactions that you have to, in theory, keep in the transaction pool and also broadcast them. So nodes need to take into consideration all these edge cases and find mitigations for how to deal with these things, because otherwise, like someone could put the network down. So, but this has to do with how much nodes trust each other and the mechanisms that they have for blocking nodes that are spamming the network and whatnot. So yeah.
One, I guess, follow-up question is like, the term memory pool implies that there's a shared memory between collators, let's say, or let's say nodes, because I'm not 100%.
The memory pool is vague. It's not part, like basically what I'm trying to say is like the state transition function doesn't know about the memory pool. Right? Like,
yeah, I know these are different layers that
so basically how, for instance, like there is no mechanism that prevents a node, a validator, from squishing the transactions that are most convenient for them um, in order to perform like a sandwich attack, right? Like they see like, oh, like the user is going to make this swap. Huh, interesting. Okay, I'm going to make these transactions out of thin air that no one has seen. I've never broadcasted these transactions. I've never done anything, but like it's fair game. I'm going to put a transaction on top of this one that brings the price up. I'm going to execute the user transaction. I'm going to put another transaction here. This is called a sandwich attack, right? There's nothing preventing nodes or validators from doing that other than reputation. Like if validators start doing that, like, you know, like people will vote them less and stuff. But like technically speaking, there is nothing in the runtime that can be done to prevent this kind of actions. Does that make sense? So how validators implement their transaction pool and which transactions they accept and how many they accept and how much they grow their transaction and whether they decide to broadcast transactions or not, it's entirely up to them. Like if a validator decides not to censorship certain transactions because they come from this address and, you know, some authority told them you cannot broadcast transactions from this address, there is nothing that can be done from the point of view of the runtime to prevent this from happening. Does that make sense? So basically, the transaction pool is not part of how nodes decide to handle the transaction pool is basically up to them.
But okay, let's say like I'm sending a transaction, I sign something, and I'm waiting for it to be approved. It's just being sent, that transaction is being shot out into the ether, and then some collator somewhere, or maybe multiple, right, are going to pick up that transaction and then produce it into a block to then be finalized. But it's out of my hands once I sign a transaction. Like,
Yeah,
right.
yeah. So once you sign a transaction and you broadcast it is that means that you are sending, like you are giving this transaction to a node that is connected to its peers, and what it's going to do is going to start a gossiping process by which this transaction, some of these peers may or may not gossip the transaction. Like what I'm trying to explain is like, if the network is functioning correctly, transactions are going to be gossiped. I mean, it's in the best interest of everyone to gossip transactions because like if you don't put transactions, like then like you know, like you don't charge fees and what, like, but there is no mechanism that can force nodes to kind of gossip these transactions or to include them into the transaction pool. It's basically there's an economic incentive to do so, but if someone creates economic incentives to prevent that from happening, then that's part of the game, I guess. Does that make sense? Is that clear, more or less? But this happens in every single blockchain, right? Like it's not. I mean, I guess the exception could be. Let's not get there. But like the exception could be like blockchains where like Penumbra and whatnot, where like you actually don't know what the outcome of a transaction is going to be because you have to go afterward. Like, you know, like anyways, completely off topic. Sorry. Okay, so sign extensions. All right. So transaction states. Who can tell me some? Just based on what we have covered thus far, who can tell me some transaction states that you can think of? Seriously? Mike, I think he said, pass the mic to.
Verified on-chain.
Yes. So a transaction can be, well, verified, I guess you mean valid, invalid, right? Like, and then if it's invalid, cannot be on chain. And if it's valid, it could have been included into block, right? That's the most basic one. But from the point of view of the user, right? from the point of view of the user, let's think of every single possible transaction state that we can imagine. Again, this is something that we covered before, but when it comes to validating a transaction, we validate the transaction against a particular block. In reality, it's not against a particular block, it's against a particular state. Again, even inside the same block, the state could change in a way that the transaction that we're going to include now it just became invalid for this block, so we have to disregard, right? Like, so that when a transaction is being deemed invalid or invalid against a particular state. So whenever we know that there is a state in which this transaction cannot be valid, then out it goes. We cannot have it in the transaction pool. But the transaction could be valid for a branch and invalid in the other. So if it's valid for a possible branch, we need to keep it around because maybe that's the branch that it will end up being canonical, right? So the first state is where a transaction is valid or invalid. Realistically speaking, there are three kinds of validity states. Whether if the transaction is invalid, that's the easiest, like it cannot be included, right? And if the transaction is valid, there are two different kinds of valid transactions. The transactions that they can be included in any block after this chain, or the transactions that are valid, but I need to wait until another transaction comes in. So it's valid, but it cannot be immediately included. I need to wait for another transaction to come in. Basically, when the nonce is too high, then I need to keep that transaction around. It is valid, but it may take some time until it gets into a block. Okay? So, yeah. But really, there are two cases, valid or invalid. Yeah? But is this understood? Like, generally speaking, like all valid transactions except for future valid transactions can be included right away. Future valid transactions, like, okay, yes, I cannot disregard it yet, but I have to wait for something before I put it into a block. Yep. Okay, once a transaction has been valid and once this transaction has been put into a block, and this is what we were seeing before, right? The result could be, the result is the evaluation of the call data, right? Like once the transaction is included into a block, then we need to compute the new state that's going to be produced by this transaction, right? Like there's the state transition function. We put the transaction through the state transition function. We apply the state transition function. We pass the current state. We pass this transaction. This is what in programming is normally called a reducer or an accumulator. Like there is a current state. There is an event. The event will be this transaction. It gets applied, and this produces a new state, right? Now, in this regard, whenever a transaction has been included, it will always produce a new state. Even if the transaction fails, it will always produce some new state. Among other things, because there is a system events storage entry that changes on each block. So at the very, very least, this transaction, even if it fails, is going to yield some events that are going to make changes on the state. Yeah. So if you think about it, every single transaction that is included in a block, in one way or another, is going to yield some state changes, right? Even if they are super basic. Now, from the point of view of the user, a transaction may be included into the block, but may fail, right? Like it may not have the outcome that I expected, right? Like I wanted to transfer this amount of tokens, but I wasn't able to because of whatever reason. Or I wanted to nominate these validators, but I wasn't able to for some reasons. Because inside the state transition function that it evaluates the call data, things could happen that prevent this transaction from reaching the outcome that the user expected. When this happens, as we saw before, it bells out, and then there is this sign extension that returns the fees to the user. But there is also another thing that happens, which is that an event gets triggered that lets us know that the transaction failed. So if we go back to my failed transaction, I don't think I'll have it. It's still here. Oh yes, it is. Perfect. So this failed transaction, if we look at the events, we will see that there is this specific event that it's letting us know that the transaction failed, and it's going to reference one of the errors. Remember that in the metadata we had information about errors. So in here it's going to reference one error. In this case, it failed because there was an underflow arithmetical error, which happened because I was trying to subtract more money than I actually have, right? So from the point of view of the user, but this is another layer, we need to take into account the transaction result. Like normally, what we need to do is like, okay, the transaction is valid, it's being broadcasted. Now what? Oh, the transaction show up in a block. Cool, got included into a block. Now, what happened to this transaction? Did it fail? Did it not? It failed. Oof. I need to let the user know that your transaction, it's been seen in a block, still not finalized maybe, but it's not going well, right? Or it did work, like, oh, it's coming, it's going to be finalized. So yeah, a transaction, what I'm trying to explain here is that a failed transaction, and this is where that, remember that before I asked, what happens if I create a transaction that sends more balance than the actual balance that I have? And intuitively, almost everyone thought like this is an invalid transaction. But it is valid. It is valid because I have enough to pay the fees. It is valid because the mortality is valid. It is valid because like every single check of every single sign extension says it's valid. It's just the evaluation of the cold data, which is not part of determining validity, that is going to fail. But the transaction is going to be valid, it's going to be included, but it won't have the outcome that we want. Yeah? So once a transaction is valid, this transaction should eventually be included into a block, and then we'll be able to determine its outcome. Yep. Cool. All right. So broadcasting. I think we have explained this before, but just let's be very clear. Broadcasting is what the library does, or whoever does, the client, whoever does, when they get a transaction and they deem it as valid, then this transaction can be broadcasted. The broadcasting is a gossiping mechanism, and it's a fire and forget mechanism, meaning that you broadcast and you don't know whether this peer, whether this node is actually broadcasting it. You know that you asked them to broadcast it, but they may internally decide, no. This guy says this is valid, but because of the blocks that I've seen, I don't think that this transaction is valid, so I'm not going to broadcast it. Another node, remember that we explained before that you can create like a mortal transaction that hangs on top of a block that there is a future block that maybe only some nodes have seen. So if this transaction reaches a node that knows about that block, right, they will broadcast it because it's like, oh, this transaction is valid. This transaction can be included into this branch, right? But maybe if it reaches another node that doesn't know about that block, then this node may decide, no, I'm not going to broadcast this because as far as I know, this transaction is invalid. So long story short, broadcasting a transaction is a fire and forget. Yes. It's, hold on a second, just one thing. It's a fire and forget event. Like you broadcast it and you hope that that eventually you're going to get some feedback about what's happened with this transaction. But this feedback doesn't come directly. It comes from looking at the blocks. Go ahead, ask the question and then I'll continue.
Is it the validators that broadcast automatically, or us as developers, we need to add some parameters that broadcast to the entire network?
Normally the ones that broadcast is like full nodes, like light node, like like when you use small dot in your browser, like small is like a light node that, despite not having a transaction pool, is able to broadcast the transaction to the peers that it's connected to. Then these peers normally, like let's think from the point of view of using a light client, which is what is optimal, right? Like you have a light client, which is a node that doesn't have a transaction pool, does not have a transaction pool, but it's connected to some peers. So this light node broadcasts the transaction to these peers, but it doesn't know whether these peers are including this transaction into the transaction pools or they are broadcasting or not. It doesn't know. Like, so far, I broadcasted to these ones. Then each one of these ones individually is going to do the same thing for the peers that they have, right? Some of these nodes may or may not broadcast it, but eventually, this transaction through this gossiping mechanism will reach a validator. Like nodes, like clients, by default, well, because they are a little bit like leeches, they economically speaking, they don't really contribute to the network. So like clients don't talk directly with validators. A like client doesn't establish a peer-to-peer directly with a validator. It establishes peer-to-peer connections with full nodes, right? Like there are many full nodes. These full nodes don't produce blocks themselves, but they evaluate the blocks that are being produced. They evaluate that they are valid. And they also have a transaction pool, and they also broadcast transactions if they deem them as right. So long story short, what happens is that once a transaction is broadcasted, from the point of view of the client who is broadcasting them, it doesn't matter if the client is a light node or a dApp or whoever, but when it's being broadcasted, you don't really know how far it reached. You don't have a way to know for sure whether it reached a validator until you see that transaction into a block. When you see that transaction into a block, then you know for sure, okay, like at least it reached that validator because that validator put it in a block. Does that make sense?
Yes, but my question is, do we need to manually state that it's going to be broadcasted, or is it automatically broadcasted from the light client? For instance, I was deploying on
No. You need to like
we need to add
as a
it to
dApp
the
developer, you use a library that does like sign and submit or sign
So
and,
we need to add it to the CLI or the.
so you let the library handle this, right? Like, so some old libraries, I should say, they rely on an RPC method of some nodes that basically do everything for you, but it doesn't do it very well, and many times it's like, so the best thing that you can do actually is to have a library that simply broadcasts, and the same library does the tracking. We'll explain why later. And the same library behind the scenes does the tracking and checks and constantly checks whether it's valid or invalid, and it communicates everything back to the user, the dApp developer. So like what I'm trying to explain is that if you use Polkadot API, for instance, this library, I'm sure other libraries also do it. What we do behind the scenes is like when we create a transaction, we send it to the signer so that they sign it. We assemble the transaction. We check whether this transaction is valid against the tip of the chain, right? And if it's valid, we proceed to broadcasting it. Now, what it's being broadcasted, we're in a pickle. Like what we know is that the transaction can't be present in any of the blocks that we have already seen, right? Like we already know about all these blocks that were created before we broadcasted the transaction. So we don't need to check in these blocks. It cannot be there, right? Like these blocks existed prior to us like broadcasting the transaction, so it cannot be there. But what we do now, every time we see a new block, we start tracking your transaction, as we'll see in a moment. And as soon as we see this transaction being valid in a block or becoming invalid in one of these new blocks, which could also happen, then we know that we don't need to look farther into that branch, right? But while that doesn't happen, we keep validating and we keep searching for the transaction, right? And always, it always ends up being settled. Like the worst thing that could happen to you is that the network is very, very busy, and that your transaction got broadcasted, that your transaction reached a validator, but for whatever reason, the validator is not including it. Or what happened not too long ago in Kusama which is that there was a this is interesting. I think it's related to this, right? There was an upgrade into some Kusama nodes and in Western too that replaced the peer-to-peer library that was used by nodes. Before they were using lib B2P, lib P2P, and they replaced lib P2P with little P2P, light P2P, sorry. They replaced one with the other. And when they replaced it, light P2P had was not fully compliant with the way that transactions are being gossiped. But thankfully, because all the Polkadot SDK nodes had the same issue, they were able to gossip them. However, the light client, which was still using the old normal protocol that is properly documented, was broadcasting transactions, but the nodes were dropping it because they were not understanding that because of this little library that got changed, right? So because of that, what happened is that when you try to broadcast a transaction on Kusama using the light client, it took forever for the transaction to be included, or it never got included. Sometimes it got included because some nodes hadn't upgraded the library, and they were still in the old version. So sometimes it managed to reach the validator, but it was kind of rare. It took a long time because you had to hit a peer that still had the old library, like the old implementation, and this peer was able to communicate with a validator that also had the old library. So this is to say that, yeah. So,
Sorry.
To the best of my knowledge, that's the only time that something like that has happened. I wish we had more of a variety of clients, because if we did, then we will find out like these issues
Well,
a lot sooner. But yeah, like this is when you broadcast, it's fire and forget. Like from the point of view of who is broadcasting the transaction, it's a fire and forget. You don't get feedback directly from there. The feedback comes indirectly from the blocks that you're seeing afterwards.
I guess just a quick statement, just from my experience using Mandala chain, I know they're a pair chain. So when I was trying to deploy a contract previously, it wouldn't be published, but it was verified and there was a transaction hash. But I couldn't see it on on their Explorer. So I had to use -- broadcast in the CLI to be able to actually broadcast it. So I just don't know if that's like a Polkadot specific feature based off Poppy, or if it's just like the parachain I had to add broadcast
I
myself.
didn't understand the question, so can you go again?
I don't know. I'm just
No,
like,
go.
I
It
had
seems
this
interesting.
whole,
It's just, I'm trying to, sorry, but like, it seems
Just-
interesting.
from my experience, it was a bit of a shit show having to add -- broadcast in my command line to be able to actually publish it on chain. So I just want to verify that Polkadot can and does automatically broadcast it, or if I as a developer need to mention anything whatsoever to be able to broadcast it. Like this is just something small, but it's like that
Yeah.
was a whole pain in the ass for me.
Okay, so let me show some code, and then we can. Shit. And then let's make sure
sorry
that
if this is considered a waste of
no,
time, but
it's
this is
it's
like
good. Like
something
I think
have
it's good that people understand how these things. So from a library perspective, right? Like so from a perspective of a dApp developer that's already using a library that's supposed to solve this problem for you. So here we have a client, and here we have a test API that it's linked. Like I'm going to call it API. An API that it's linked to this client, right? So if I go here and I do transaction.system.remark or balances or whatever, right? Let's do a remark. Then here I can pass like a remark, which is binary data, I don't know, from text, hello, right? So from this, I can do a number of things. I can sign the transaction and broadcast it later. Like sign means like I'm going to create a signed transaction out of this, right? And I may broadcast this transaction later. I can sign and submit the transaction. It's like I want to sign it, and I want to submit it. And I want you to give me a promise that will resolve once this transaction is found into a best block. I can also sign, submit, and watch. So sign, submit, and watch, basically what it does is I pass, here I pass a signer. I need to pass like a signer that I have from my extension that I have created manually using novel curves or whatever. And then here I can go subscribe if I want to, and then and I can listen to the different events, and then I can have event.type, and then it's going to let me know when it got signed, when it got broadcasted, if it was included into a best block, whether it got finalized, and each one of these events, the payload is going to be different depending on their state, right? Like, so, okay, but now your question, if I understood it correctly, is like, what happens if I already have signed the transaction? I have to pass a signer here. I'm going to cheat. I'm going to pretend I have a signer, right? So this is const my TX. So this transaction, this transaction is binary data. Well, like if the transaction is valid, but if I just create it, like no one knows about it. Now, you can go and give this, put it in a USB if you want, and give it to someone else, or like send it through email, whatever. But it won't be until a client actually broadcasts this transaction that is going to reach the network. So sometimes, some people, they choose to create this transaction in an offline environment. Actually, our library gives you a very good util for doing that. And then they go to a client like this one. Let's see. And then they go client dot submit. Submit basically means broadcast. If we look at the docs, it says broadcast the transaction, promise based, the promise will resolve data. And then you also have submit and watch, which is the same as before. Like one is promise based, the other one is observable based, right? Like if you just want to know, like just let me know when it's included into the finalized block, that's cool. If you want to know all the intermediate steps, then you can watch it. But this submit and watch, what it's going to do is going to, if we look at the submit and watch, what is it going to do behind the scenes? Step one, validate the transaction. It's going to validate, like, is it valid? Yes. Okay. If it's valid, I'm going to sign it. Now, you may ask, what happens? I'm going to my transaction, right? What happens if when I subscribe, right, the transaction is invalid, right? So here you have next. Next is for when we receive, or you don't need to use next. You can use like the deprecated overload. So here you have events. These are events for when things are going well, okay? Or error. Like this is a callback that will get called when there's an error. Now, if you look at this error, sadly in TypeScript, like typing errors is a bit of a pain, but you could go here and do if error instance of invalid TX error, right? This error happened because the transaction is invalid, right? So if the transaction is invalid, most of the times, if the transaction is invalid, you will never see the event type signed. Not always. Sometimes the transaction is going to be broadcasted. This transaction in this case has already been signed. And sometimes we're going to broadcast the transaction. So this is going to give you the event flow, right? Like it's going to tell you, I'm broadcasting this transaction, yeah? And I'm going to let you know what happens next. But it could happen, it's rare, but it could happen. It's like you broadcast a transaction because right now it looks valid. And while you are searching for this transaction into the upcoming blocks, you realize that now this transaction, it became invalid everywhere. Maybe because in the moment that you broadcasted that transaction was only valid into a branch that now got pruned. Yeah? So now the transaction become invalid, and it could happen that after a transaction becomes broadcasted, that it eventually triggers an error with invalid. Like as soon as we know that this transaction is invalid and that it cannot be valid again, meaning like we've seen it invalid into a block that now is finalized, then we stop the process, we trigger an error, and whether it's a promise or an observable, it's going to give you an error that's going to be, hey, this transaction is invalid, and then in here, you will be able to, because you check the instance, TypeScript will help you, and you will know the cause, you will know the message, you'll have like, you know everything that you need to know about why this transaction became invalid, yeah? So, similarly, another thing that could happen is that the transaction type, like the event type, sorry, is equal to transaction is in the best block state, right? And now you look at the event, and then it's like, oh, it's in the best block state, but is it found or not? So it could be that it's in the best block state, but it's invalid. So if it's found, is that it is valid. Like it's like transaction is there. If it's not found, it's like in this best block, it's been deemed invalid. But if it's found, you can the type assertion keeps going, and you check. It's like, oh, if it's found, now here you have all the information that you need. Was this extrinsic successful? Now we look at the events. Is it successful? Is it unsuccessful? Which are the events for my transaction that now it is included into a block? Does that make sense? So the library, our library tries to provide you with all the insights that you need in order to track a transaction. If you don't want to track all that stuff, all you want to know is like, just let me know once it's in a finalized block, then you use the promise base. And if there's an error because it's invalid or something, it will reject. And if it's eventually included into a block that it's finalized, it will resolve. I hope that makes sense. But like, yes, like basically the library behind, but what I'm explaining is what the library does behind the scenes. Because like, if you understand what's happening behind the scenes, that always allows you to create better dApps. Like to understand what is the state flow that a transaction goes through will help you create better user experiences, and it will also help you to better understand what you are capable of doing. Like for instance, you may be listening to best blocks and finalized blocks, but maybe now you're listening to a block that is not best, it's not finalized, but for some reason it puts the state of the chain in a state that it's very interesting. And now you may want to create a transaction on top of that block using mortality, as we explained before. And then if you're lucky and in the end that transaction becomes part of the canonical chain, then your transaction will be there. If not, your transaction will be invalid, no harm done, right? Anyways, I'm just trying to, please ask as many questions as you want. I just want for you to understand what are the things that are happening behind the scenes. That doesn't mean that you as developers will have to code this. This is already solved by libraries, but again, having the insight of what happens behind the scenes, it's going to empower you as app developers, I believe. Yeah? Cool? Cool. All right. The heck? Okay, here. Okay, broadcasting. Okay, once a transaction is deemed as valid, it can be broadcasted. Broadcasting is a fire and forget, as we said before. And then once it's, yeah, okay. So once we realize that one transaction cannot be valid again, we need to stop broadcasting, inform the user, and stop the tracking process. Okay, now let's look at the transaction tracking process in depth. And then we'll have some extra time. And I don't know if I should give you the exercise or, okay, we'll see. Okay, so pay attention, because after this, you're going to have to solve an exercise that it's basically about tracking transactions. Because I think that if you solve this, you will, I mean, when someone explains and spoon feeds you like everything, everything makes sense. But if you have to solve it on your own, then I think that it's when the knowledge kind of gets like really ingrained, right? So pay attention to this. All right. So transaction tracking. This is the process by which we, after we have broadcasted a transaction, we remember broadcasting the transaction is a fire and forget process. So now we need to track this transaction into the upcoming blocks that we're going to see to know what is its fate, right? What's going on. All right. So let's see this, right? Like First, let's realize that the blockchain, from once something is finalized, there are no branches, right? Like once something is finalized, there's only one chain. But above what it's finalized, there can be forks, and sometimes there are more than you may expect. In the future, there will be less because there is don't worry, like it doesn't matter. Like the things like forks occur, and you need to take them into account. So you may have a fork that it's like the best. Actually, this is wrong. It should be best because it's higher than the others. So this block should also be part of the best blockchain. But like this is like the best blockchain, and this is a fork. And these are prune blocks, right? Like this is a fork that happened. That finality determined that it's not part of the canonical chain. So we can forget about this. You saw it, but like this is to be disregarded. But everything above this is potentially going to be part of the canonical chain. We don't know for sure. From the point of view of our node, it kind of looks that this one is going to be the winning one, but we won't know for sure until later. So we need to take everything under consideration. Okay. So transaction tracking starts at a certain point. Like when we start broadcasting a transaction, we know that the transaction cannot be present in any of these blocks because these blocks already happened, obviously, right? Like if they were already present, if I already saw these blocks before I broadcast the transaction, my transaction cannot be included there. Once it's broadcasted, then is when I have to start, well, sorry, before I broadcast it, again, I need to validate it against the finalized block and against the tip of all these known blocks. If it's valid against one of these states, it's fair game, I can broadcast it. Cool. Transaction lifecycle. Validate beforehand against the tip of the chain and broadcast it if it's valid. And now we need to track it inside the incoming blocks until there is a finalized block where the transaction is either included or invalid. Right? Once we have a finalized block where the transaction is part of that finalized block, then we can stop the tracking process, or if one of these ones deems the transaction as invalid, we can also stop, and it's invalid, and we're done. Yes? So this is not a real term, but we are going to use this term that it's settled. Like settled means that you don't need to look far. Like once the transaction is included, or like once we find a block in which our transaction has been included, or once we find a block in which our transaction is no longer valid, we don't need to look farther into the descendants of that block because we're done. Like the transaction has been settled at least for that branch, right? So once the transaction is settled into a block that becomes finalized, then we finish the tracking process. All right, transaction tracking. In order to track a transaction, what we need to do is for each new block event that we receive through the JSON RPC, driving nuts this camera. Anyways, from each new block event that we receive, right? We are going to check, is this block the descendant of a settled block? Right? Settled block, remember, settled block means a block in which we have already seen that the transaction is found or is invalid. If it's the descendant of a settled block, we ignore this block. There is nothing for us to check, right? Like because it's already part of one of its ancestors. So it's settled, we ignore it. If it's not the descendant of a settled block, then we need to find out whether we can settle the transaction in this block. And for that, we're going to first check, is the transaction present in the body? So we check. If it's not present, we ignore and we keep searching. If it's present, then we flag the transaction for this block as settled. Oh, sorry, that's not, I explained it in the other order. Sorry, I was explaining this case. Anyways, if the transaction, the first thing that we do is like we check if the transaction is present in the body. If it's not present, then the next thing that we need to do is check, okay, maybe it's not present because it became invalid in this block, right? So let's check. If it's invalid, Then we flag this as settled and invalid. If it's not, we ignore it and we keep going. The other branch is like, is the transaction present in the body? Yes. Okay. We go and we check whether it's successful or unsuccessful from the event. But the important thing is like we flag it as settled in that block so that we don't keep looking any farther, right? So this is what we do every time there's a new block. And then every time there is a finalized event, we need to check, hey, is this finalized event finalizing a block that got settled, a block in which we saw the transaction as invalid or as included into the block? If the answer is yes, we are done the tracking process. We have already reached the end. Now we just let the user know what's the outcome of this transaction, whether it got included, whether it was not included because it's invalid, whether it was included and it was successful or unsuccessful. We communicate all that stuff to the user, and we're done searching into blocks and whatnot. And we also stop broadcasting it, of course. If it's not, we ignore and we wait for another finalized event that puts our transaction as settled. Okay, so that concludes the transaction tracking. I hope that you paid attention because we're going to solve an exercise that basically you're going to be tracking transactions and determining what their state is at every point of these events. Now, last but not least, if you look at the JSON RPC spec, you are going to see that there is a group of functions that is called transaction watch. And transaction watch seemingly already does all this stuff for you, right? Seemingly, transaction watch is a group of it has a group of functions, submit and watch and unwatch, that lets you know about all this stuff. However, we don't find this group of functions very useful, or as useful as people may think. Who can give me a guess of why we don't like this group of functions so much? It's difficult to find out, but anyone can give a guess of why we are not using this. So basically, Papi doesn't use this group of functions. Papi uses broadcast, and then it manually tracks transactions. We don't use this. Who can guess why? No one, right? The reason is that, remember that we explained that transaction, like groups of functions, could be implemented. Like one of the reasons why we have different groups of functions is precisely so that we can have gateways and load balancers, and we can have one node implement one group of functions, another node implement another group of functions. So the problem with transaction watch is that the events that we receive from transaction watch are not in sync with the events that we receive through the chain head group of functions. So in the chain head group of functions, we know like, hey, we see this log, this is finalized. And let's remember, as we explained before, in the chain head group of functions, we need to keep track of the pin blocks, because among other things, when we're talking with a light client, we have to get rid of blocks that we're no longer using, because otherwise the light client is going to run out of memory. This is something that the library does behind the scenes for you, but it's something that needs to get done. Now, what happens when, like you get a block, this block gets finalized, the user is not requesting any data for this block, well, you will unpin this block, right? But then what happens if later on you get a notification from transaction watch that's like, oh, by the way, that transaction that you broadcasted before, I just deem it finalized in this block here, but you no longer have that block. So the big problem that we have with transaction watch is that it's because it's implemented in a different group of functions than chain head, we don't have any guarantees about in which order the messages are going to arrive. And that puts us in a situation where we have to deal with impossible race conditions. Ergo, we cannot rely on it. If chain head was, if there was a group of functions that was like chain head, but with a superset of chain head that also had this, then we will be able to use it. But because it doesn't, we can't. Because the only option that we could use it would be by keeping a lot of blocks pinned in Eternum while we wait for that one. So it's very inefficient. It's a lot. Also, in the end, what transaction watch does is basically the same stuff that we do. So if we are using the light client and we don't use transaction watch, we are freeing the light client from using those resources. We handle it ourselves and we're fine. But the main reason what I'm trying to explain here is that the main reason why we don't use transaction watch, for starters, like there are other reasons, but like the main reason is that we cannot guarantee the synchronicity between events of chainhead and the events that we get from transaction watch. There are some GitHub issues with long discussions about why this is stupid, but whatever. Like that's the main reason. And another reason is like because some of the states that it produces are neither here nor there. Like we need more information on some of them, so that's why we go low level and we handle everything ourselves. Okay? Questions about this? Nope. Oh, okay. Yeah, here I have a slide explaining the problem. So yes, this is what I said before. Transaction watch is detached from chain head. So we may receive blocks. Right, this is the other case. Right? Like we may receive blocks from transaction watch that we have not seen in chain head yet, which puts us in an awkward situation because we cannot reconcile these two, and now we have to create block pressure and whatnot. We can also receive a block that we saw, but now it's unpinned. So it's not that useful. Like it could be useful not for a dApp, but like if you have a tool that the only thing that it does is like broadcast transactions and see the outcome for something like that, sure, you may use it. But if you need to combine the broadcasting of the transactions with the state that these transactions produce, which is what most dApps do, right? Like you probably, when you have a dApp and you broadcast a transaction, you're going to have some optimistic state of how you expect this transaction to affect the state of the network and whatnot. So you need to combine the state of that this transaction could produce into the chain with the state that you have in your dApp. So for those use cases, we cannot use transaction submit and watch. Sorry, how is it called? Yeah, transaction watch, because it's not synced with chain head.